You think the speed of light is just a number? 299,792,458 meters per second? Fast? Really fast. The fastest thing we know. Fine, but why is it the limit? Why can't you go faster? What actually stops you? Most people have never really thought about this question. They just accept it. Einstein said so. Speed of light is the cosmic speed limit. That's just how the universe works. But that's not an answer. That's just repeating words you've heard. When you really ask why nothing can go faster than light, when you dig into what's actually stopping you, you discover something so strange, so fundamentally different from everyday experience, that it changes everything you think. You know about space and time. The speed of light isn't just a speed. It's not just the fastest thing. It's the structure of the universe itself. It's woven into the fabric of space and time in a way that makes going faster, literally, meaningless. Not impossible, meaningless. Let me show you what I mean. Let's start with something simple, something everyone knows. Things fall. Drop something. It falls down. 16 feet in the first second, to be precise. That's what Galileo measured centuries ago. Drop a ball, drop a rock, drop anything. In 1 second, it falls 16 feet toward the ground. Now the moon is going around the Earth, orbiting. It's not falling down, it's staying up there, going in a circle endlessly. But wait, is it falling? Think about it carefully. If the moon were just sitting there in space, stationary, not moving, what would happen? It would fall straight toward the Earth. Gravity would pull it directly in. But the moon is moving. It's moving sideways, tangent to its orbit, perpendicular to the direction toward Earth. And because it's moving sideways fast enough, while gravity pulls it down toward Earth, it keeps missing the Earth. It falls toward the Earth continuously, but keeps missing. That's what an orbit actually is. Continuous falling while moving sideways, fast enough to keep missing. Perpetual falling that never lands. Now, here's where Newton had his brilliant insight, the connection that changed everything. The moon is 240,000 miles from the center of the Earth. We're standing here on the surface, 4,000 miles from the center. So the moon is 60 times farther away from Earth's center than we are. 60 times more distant. Newton said, what if gravity gets weaker with distance? What if it follows an inverse square law? That means if you go twice as far away, gravity becomes 4 times weaker. 3 times as far, 9 times weaker. The square of the distance. If that's true, then at the moon's distance, 60 times farther away, gravity should be 60 squared times weaker. That's 3,600 times weaker than at Earth's surface. Now, on Earth's surface, things fall 16 feet in 1 second. If gravity at the moon is 3,600 times weaker, then the moon should fall toward Earth by 16 feet divided by 3,600 in that same time. Do the math. 16 feet divided by 3,600. That's about 1/20th of an inch per second squared. Actually, let me be more precise about this calculation. In 1 second, the moon's path curves toward Earth by exactly that amount Newton predicted. Newton calculated how far the moon should fall toward Earth in 1 second if gravity follows an inverse square law, and it matched perfectly with observations. The moon is falling at exactly the rate Newton's law predicts. Not approximately exactly. This was absolutely huge. This wasn't just some speculative theory. This was a concrete prediction. Newton took a completely independent fact, how fast things fall on Earth's surface, and connected it to another completely independent fact, the period of the moon's orbit and its distance from Earth. Two things that seemed totally unrelated, completely separate phenomena, suddenly became connected by one simple law, the law of gravitation. There was no going back after this. Now, Newton went further. He calculated what the shape of planetary orbits should be if gravity follows an inverse square law, and he found that they should be ellipses, perfect ellipses with the sun at one focus. And guess what? Planets do move in ellipses. Kepler had already measured that empirically through decades of careful observations. But Kepler didn't know why. He just knew they did. Newton explained it from first principles. He derived the shape from the force law. He got 3 major confirmations for the price of one calculation, as it were. And then more things fell into place, one after another. The tides. Why are there ocean tides? Because the moon pulls on the Earth. But wait, if the moon just pulls the Earth uniformly toward it, there should only be one high tide per day, right? The bulge of water on the side facing the moon, one tide, as Earth rotates under that bulge. But there are 2 tides per day, every 12 hours roughly. 2 high tides, 2 low tides. Why 2? Some people thought the Earth was pulled away from the water on the far side. Others thought the water was pulled toward the moon on the near side. Both were sort of right. But neither got it completely correct. Newton realized what was really going on. The actual mechanism, the force of the moon on the Earth and on the water depends on distance. The water on the near side, the side facing the moon, is closer to the moon than Earth's center is, so it gets pulled harder toward the moon. And the water on the far side, the side away from the moon, is farther from the moon than Earth's center is. So it gets pulled less strongly than Earth's center does. So you get 2 bulges of water. One where the water is pulled more strongly toward the moon than Earth's average. One where the water is left behind because Earth's center is pulled more than that distant water. 2 tides per day from one moon. Explained. Actually, to be more precise, the Earth and Moon both orbit their common center of mass, which lies inside the Earth, but not at Earth's center. If you want to think about it in terms of centrifugal force, in the rotating reference frame, the water on the far side is thrown outward more than Earth's average. Either way you analyze it, 2 bulges, the mathematics works out. At any rate, the tides were explained completely, and the fact that there were 2 per day made perfect sense. A lot of other phenomena became quite clear under Newton's framework. Why is the Earth round? Because gravity pulls everything toward the center equally from all directions. Why isn't it perfectly round? Because it's spinning. The rotation throws the equator outward a little bit, and it bulges there until forces balance. Why are the sun and moon round? Same reason. Gravity plus rotation determines the shape. Now, as science developed over the following centuries and measurements were made ever more accurately, the tests of Newton's law became much more stringent, much more precise. The first really careful tests involved the moons of Jupiter. By careful observations of the way they went around over long periods of time, astronomers could check very carefully whether everything was according to Newton's laws. They measured positions night after night, calculated orbits, made predictions, and it turned out not to match perfectly. There was a discrepancy. The moons of Jupiter appeared to get sometimes 8 minutes ahead of their predicted schedule and sometimes 8 minutes behind the schedule, where schedule means the calculated positions according to Newton's laws applied precisely 8 minutes. That's a huge discrepancy when you're making precise astronomical measurements. Something was clearly wrong. Either the law of gravitation was incorrect or something else was going on. But wait, someone noticed a pattern. The moons were ahead of schedule when Jupiter was close to the Earth in its orbit and behind schedule when Jupiter was far away on the opposite side of the Sun. Rather odd circumstance. Not random errors, but a systematic pattern correlated with Earth-Jupiter distance. A man named Romer, having confidence in the law of gravitation, having faith that Newton's law was correct, came to an interesting and profound conclusion. It takes light some time to travel from Jupiter's moons to the Earth, What we're looking at when we observe the moons are not how they are right now at this instant, but how they were some time ago. The time it took the light to travel from there to here. When Jupiter is near us in its orbit, closer to Earth, it takes less time for the light to travel. When Jupiter is farther away on the other side, it takes longer for light to reach us. So Roma had to correct all the observations for the differences in light travel time, and by analyzing how much the moons were ahead of schedule or behind schedule, he was able to determine the velocity of light. He calculated it from astronomical observations. This was the first demonstration that light was not propagated instantaneously across space. Light has a finite speed. It takes time to travel. Think about what just happened here. This is remarkable. We found the speed of light not by measuring light directly, not by timing light beams, but by having confidence in the law of gravitation. When something didn't match Newton's predictions, instead of throwing out Newton's law immediately, Romer said, what if light takes time to travel? What if there's a delay? And he was absolutely right. I bring this particular historical episode to your attention because it illustrates something profound about how science works. When a law is right, when you've got a correct fundamental principle, it can be used to discover another one. By having confidence in Newton's law of gravity, when something appeared wrong, it suggested perhaps some other phenomenon was at play. And if we had not known the law of gravitation with such confidence, we would have taken much longer to discover the finite speed of light because we would not have known what to expect from Jupiter's satellites. This process of discovery has developed into an avalanche. Each new discovery provides the tools for much more discovery. Each insight opens doors to more insights. And this beginning with Newton and Roma. It's the start of that avalanche, which has gone on now for 400 years in a continuous accelerating process, and we're still avalanching along at high speed at this very moment. But here's the thing that changes everything. Once you know the speed of light exists, once you measure it carefully, you start noticing something very, very strange about it. Something that makes no sense at all, according to common sense. Light always travels at the same speed. Always. No matter who measures it, no matter how fast you're moving when you measure it, no matter what direction you're moving. Let me make this concrete with a thought experiment. You're standing still on the ground. You shine a flashlight. You measure the speed of the light coming out using precise instruments, are 299,792,458 meters per second. Fine. That's the speed of light. Now you get on a train, a fast train, moving at, say, half the speed of light. Incredibly fast, but theoretically possible. You shine the flashlight forward in the direction the train is moving, pointing ahead. Common sense says the light should now be traveling at the speed of light plus the speed of the train. Just like if you throw a ball forward from a moving train, the ball moves faster relative to the ground than if you threw it. While standing still, velocity should add, but that's not what happens with light, not even close. You measure the speed of the light beam carefully. It's still traveling at 299,792,458 meters per second, exactly the same speed as before. Unchanged. You say, okay, maybe I measured wrong.